Hey guys, um, this lecture is going to be focusing not on our ancestors so much, but of more recent um, human groups leading into actual humans that live in more modern cities throughout the Industrial Revolution. But leading up to that, we're going to talk about some more ancient civilizations. That eventually get into the European conquest of North America and how that was also showing and highlighting how humans interact with their environment. So we're going to start off with these civilizations from like 5,000 years ago and move more into the last few hundred years with European settlers coming to North America, and then finally getting into the Industrial Revolution, which was set into motion by the agricultural revolution of the time. So we will talk about all of this in today's lecture. So, like I just mentioned, we're going to focus on more modern human interactions. We're going to talk about natural processes that occur naturally that do engage with shifting the environment. We're going to focus more on the greenhouse gases and how greenhouse gases are associated with the greenhouse effect. And then we will talk about some irrefutable evidence supporting anthropogenic climate change. And then we will begin studying the effects of climate change, which is a main goal of this unit, is to talk about these larger scale effects happening in present day. So starting with this slide, we're going to focus on these ancient civilizations that we already kind of mentioned. We talked about ancient Egyptian and ancient Mesopotamian civilizations that set up on these river valleys in this area. Obviously, those river valleys would flood seasonally, allowing them to grow crops that were quite healthy, given that those sediments were nutrient rich. But what we should note is that 5,000 years ago compared to today, the continent of Africa was different ecologically. So we can say that 5,000 years ago, we have different shades, and these different shades resemble different ecosystem types. And we're going to get into different ecosystems next unit, but basically we should know is that in present day, we have the Sahara Desert, this extreme desert at this latitude, really, really hard to live here. But 5,000 years ago, this was a semi-desert. It was wetter. There was more plants, and then the most northern tip of Africa was actually Mediterranean scrublands, which are a transitional ecosystem in between semi-deserts and forests. So you do get trees over here, and then over here you actually do have intact Mediterranean forests. So that's really cool. You could easily see the importance of these ecosystems of the time. Now, when we think of ancient Egypt, we don't actually think of shipbuilding. When you hear like Vikings, you know that Vikings, they built ships. When you hear about, the more present day British Navy, in the 1700s, you think of shipbuilding. But ancient Egyptians, they had really good ship technology. And that actually is kind of understated throughout the ancient Egyptian civilizations, is how good their ships were. So here's an ancient Egyptian ship. on the Nile. They were rather big. They did have sails. And, ancient Egyptian was a huge civilization for thousands of years. So they needed means of transporting goods in and out. So they used wood to build these large ships, and they got their wood from these ecosystems. Obviously, as time progressed, this area became drier and drier. These forests kind of retreated, and no longer did you have the means, the timber to actually make these ships. So, and another unit we're going to learn about is actually dealing with forest management. And I do touch on this in forest management, but ancient Egyptians actually had to travel to other places like Lebanon to get their wood, right? So on the Lebanese flag, there is actually an ancient cedar tree. So here's a cedar tree right here. And ancient Egyptians absolutely pillaged many parts of Lebanon for their timber to produce their wood. So this is like a preface of civilizations actually causing deforestation as their settlements grew, as they increased their transportation and the importation of goods and the exportation of goods. They needed more wood resources to actually build ships to move these products around. And as we get into more present day, before we get into more present day, we should talk about the Greeks. So the Greeks too, they utilized wood, and they utilized wood so much that they caused major deforestation across their land. And something very interesting comes up. So like when you hear of Greek food, there's not a lot of beef in traditional Greek food. There is, however, a lot of lamb. So ancient Greeks, they actually reduced their forests, and they actually created a very barren landscape that cows simply could not live on. Now, goats and sheep, they actually eat some of these hardier plants that grow in these deforested, drier, arid Mediterranean ecosystems. So it's interesting to me that the reason why you see so much lamb and goat in traditional Greek cuisines is because of the way they interacted and deforest their land. So I think that's really interesting. Progressing through time, we finally get into the 1700s. You know of the British naval fleet was easily the best of the time. Portugal obviously had a very good fleet as well. But the British naval fleet had these massive ships made of wood. They had these huge masts, and to maintain this fleet of these naval ships, they had to use so much wood. And Britain actually ran out of forests to maintain these ships. And before I get to the next slide, I just wanted to show you what herbivory does. So here we have this fence, and if you have grazers like those sheep and goat that I was talking about, when they are excluded from an area, you get a totally different plant assemblage. So that also highlights how humans manipulated their land. As we would eat these meat products, those animals, they need to eat as well. And without a barrier, they're totally changing the landscape, right? So, I mean, you could see that this land, it actually holds on to less water than when you put up a barrier. So there's that indirect interaction with the land as well. segueing back into the shipbuilders. So this was actually a main reason. Here's another picture of a naval boat, a British naval ship. A main reason why they even came to North America in the first place was that the original settlers had realized that there were massive trees up along the East Coast. So the eastern white pine, for example, was a prime tree species that the naval fleet of Britain wanted to gain access to. Because there was limited materials, the only substance that they could create their masts from was actually single trees. So these eastern white pines, they grow really straight, they grow really tall. Those are perfect for the masts of these ships. So they, and this is the distribution of eastern white pines. They have a relatively large distribution, and the British fleet, they wanted to gain access to this wood. So for all you history buffs, there actually was a pine tree riot of 1772 in which tensions between the British and the New England colonies actually increased as these Brits they set these laws and said that, like, you guys can't cut down these trees. These trees are for the king's fleet. And they're like, we need to use these pines too. So tensions increased and they adopted this flag. And some historians think that this was actually one of the catalysts of the increased tensions of the time. So this is a modern representation of the flag. I think that's really cool, showing the white pine as well as the roots, which I think is super cool looking. But yeah, they did not like the way the British powers were kind of just saying, yep, these are our trees. We need them. We need to create them for our ships to maintain our fleets. And there was this riot where they didn't actually allow the Brits to take their eastern white pines. Eventually, the fleets are not maintained readily, and that eventually causes the demise of British power. It's just not having enough ships. So here is eastern white pine, what it looks like. So if you're on a hike and you do find a pine tree, take a look at its needles and a bundle of needles on a branch. And if you take a closer look at a bundle of needles and you count 5, like right here, you are definitely looking at an eastern white pine. And these pines had not only a significant cultural significance to the British people that needed them to build their ships, but Native Americans actually highly regarded this species of tree. So the Iroquois, for example, they really loved this tree. It was like a sacred tree to them because there was 5 tribes of the Iroquois, and they thought that each one of the needles actually represented each of the 5 tribes. Another interesting point here is that humans, even though, these are relatively modern humans, right? I mean, anatomically, we are the same. But there wasn't a really good understanding of the actual ecosystem. So even though Native Americans at the time loved and regarded this tree as sacred, they didn't ever plant them. And they would cut them down to use them. So it's interesting that even though they're, this sacred tree, there is no management for these forests in place, right? And unfortunately, it takes just massive amounts of deforestation and years of environmental collapse for us to realize our role with these forests. So now we're going to fast forward a couple hundred years, actually just, starting in the 1800s. Here's this video. I'll put this in the link below. It's about how modern human advancements have had a large impact on the environment. But the first thing that I want us to get clear is that the Industrial Revolution is only put into place because of the Agricultural Revolution, right? So there are many things that occurred during the Agricultural Revolution that allowed humans to it allowed fewer humans to produce more food. So things like tractors and fertilizers and different mechanisms and just knowledge about the land and the different crops throughout the 1800s allowed more people to move into cities. So before the Agricultural Revolution, people had to grow their own crops. There were families, there's family complexes, and two people would have like 12 kids to work the farm because they had all this land, they had all this corn and cabbage to grow and preserve throughout the winter months. But as with these agricultural advancements, people moved away from farms. Fewer people, again, could help produce more and more food, which allowed people to do other jobs, which allowed people to move in tightly packed cities and do other things rather than just farm. So we're going to learn about some major other technological advances of the time. But what we should know is that this is a positive feedback, right? So again, another underlying theme of environmental biology is this positive feedback, or kind of this snowball effect, right? A snowball that is rolling down a hill with snow on it is going to get larger and larger and larger. It's going to have this positive feedback. And in regards to this, I'm talking about how with advancements increasing and continuously increasing, you're going to have more and more people moving into cities. With more and more people moving into cities, there's new factory jobs. With more factory jobs, there's more GDP. With higher GDP, people are buying and producing more things. And as we learn, the production of these things increases these greenhouse gases, which increases the temperature. So it's related to the climate in a very intricate way, right? So more and more people are going to produce more and more greenhouse gases. And this, as we produce more, our population increases and we get this positive feedback. So on to some of these kind of specifics of the Industrial Revolution. We have the advancements of textiles. So this is past the agricultural revolution into the Industrial Revolution. You had new machines creating fabric on a huge scale. So the mechanized cotton spinning powered powered by steam or water increased the output of a worker by a factor of around 500. So that is a huge leap in the production of textiles. Now, the power loom increased the output of a worker by a factor of over 40. Again, huge leap. The cotton gin increased productivity by removing seeds from cotton by a factor of 50. Again, times 50 times, right? Absolutely nuts. These three things that have to do with textiles greatly increase the textile production across our planet. Large gains in productivity also occurred in spinning and weaving of wool and linen, but they are not as great as in cotton. So cotton at the time is just a booming industry. You can't talk about the Industrial Revolution without talking about steam engines. So steam engine is a heat engine that performs mechanical work by using steam as the working fluid. Now, steam sounds clean, but we have to know that coal is what's heating up the water to create steam, so it's not clean at all. Now, the adaptation of a stationary steam engine to rotary motion made them suitable for industrial uses. So they realized that by pumping steam through this mechanism, you could actually spin this turbine, this rotary motion, and then you can apply this rotary motion to so many things, right? So this was a great advancement. This actual rotary motion makes steam power just a really broad use. Now, there was also advancements in iron making. Iron has amazing qualities of strength as well as flexibility. The substitution of coke, which is this material, for charcoal greatly reduced the fuel costs of pig iron and raw iron products. So instead of using charcoal, they would use a substance called coke, and that burned hotter, it burned longer, and you could have a better end iron product, right? Machine tools such as the planing machine actually help create more tools. So we get these products that can cut and shape metal into shapes, additionally, and finally producing more and more tools. So tools that actually create tools is another great example of a positive feedback. We had gas lighting. So obviously there was lighting before electricity, and the purification and storage of gas byproducts allowed factories to work around the clock. They had gas lamps, and this allowed these factories to run through the night. No longer were you limited on sunlight. And this actually allowed the first city nightlife too. Transportation is a huge one. And in this area, if you're from Buffalo, you should know about the Erie Canal. The Erie Canal and canal systems occur before railroads and well before just regular roads. So the Erie Canal, we owe the Erie Canal to this area's success. So this area that I'm circling over here is known as like the Rust Belt. And the Rust Belt was this heavily industrialized area that was, all these factories along these waterways were then connected via the Erie Canal. So the Erie Canal actually connected the entire Rust Belt to New York, to actually the Atlantic Ocean, so Europe as well. Because boats could traverse the Great Lakes, right? And then move across the Erie Canal and down the Hudson River to Long Island and the rest of the eastern seaboard. So the Erie Canal was this development. Transportation, again, a great example of a positive feedback. The more things you are allowed to move around readily, the faster you're going to be able to produce things. Population's going to increase, and greenhouse gases are too going to increase. So I really like the fact that throughout New York, you have major cities of clearly the major cities of New York are going to be along the Erie Canal, right? So we have Buffalo, we have Niagara Falls, we have Lockport, right? Again, Lockport, if anybody's from Lockport, as the name suggests, Lockport has a lot of lock. So a lock is this mechanism that allows a canal to traverse an area that has different elevations. So say there's a hill, right? The canal, the water will stop, right? But these locks actually, there are these little compartments that a boat like flows in a lock, the door comes up behind it, and the water flows up, making the boat rise up, and then it gets to another level of elevation. It goes a few hundred yards, depending on the elevation of that area, and then it'll enter another lock, and it can traverse these changes in elevation. Lockport is known to have many changes in abrupt changes in elevation, which is why they adopted the name Lockport. So there's a lot of locks in Lockport. We have Rochester. We have Oswego. Now, this doesn't look like it's right on the Erie Canal, but look, we have this Oswego River right here. So that is, in fact, a connection to the Erie Canal. We have Syracuse, again, connected by these waterways. The Great Lakes, too, are going to be connected here, most of them. Through the Oneida Lake, we have Rome, New York, Albany, Waterford, and then obviously the Hudson River down to New York City, Long Island, and the rest of the eastern seaboard, right? So this connected not only New York, but the entire Rust Belt, the entire Great Lakes system, some of Canada, right? And greatly increased the GDP of the area. Now, this figure is the actual railroads. So railroads greatly increased the transportation, decreased the time of transport. So railroads and trains were just much faster. Once we get these set up, we are moving products faster and faster. And the Erie Canal is kind of abandoned once we get the railroads set up. In modern day times, we have this figure, which is the roads, the major roads of the United States. I mean, it's just wild that, when I was a kid, I would have to, I wasn't driving yet, but my parents would have to search, and they would print out this piece of paper that was turn by turn directions when we would go on vacation. We always got lost, right? I mean, it never failed. Making a wrong turn. Nowadays, we put it on our phone. We don't even think about it, right? So I have friends that, have done road trips that they didn't look up the route they were going until the night before, right? So it's just crazy that with our phones now, we don't have to know the roads. We put it on our Bluetooth speaker, and we can get to the West Coast. Obviously, it'll take a decent amount of time, but it's just wild how connected our roads are and these methods of transportation. Now here's another canal system. This is the Grand Canal, which is much larger than the Erie Canal. This is in China, and we have over 1,700 kilometers, over 1,000 miles of canal systems. Really, really crazy. Again, the goal here is to talk about this positive feedback. More and more goods were produced. This increased demand, and people away from city centers could attain these different products. No longer did we have to produce our own food. So this encouraged people to move away from an agricultural life and more into a city life. These advancements increase GDP, right? And across the planet, you have these increases in GDP, right? GDP per capita, the amount of money the average person gets, increases greatly in the 1800s with the setup of transportation, past the agricultural revolution into the industrial revolution. You get these sharp increases in productivity, in products, in transportation, and in ultimately GDP. Now, what coincides exactly with this is the increase in greenhouse gases since industrialization. You can see they are relatively the same. These three greenhouse gases are relatively the same from 2,000 years ago all the way up until the 1750s and 1800s. And then once we get the Industrial Revolution, we get this sharp increase, this kind of exponential growth in CO2 parts per million. So CO2, this red line is for parts per million. Nitrous oxide is the blue line, which is in parts per billion. And then CH4 or methane is also in parts per billion. So we can see sharp increases in these major greenhouse gases, which then correlates to temperature. So temperature does change more randomly through time as compared to these greenhouse gases. But we are going to learn about why temperature and what causes the temperature to change on Earth. But still, even with all of this, you can see starting in the 1800s, again, another extremely sharp exponential curve when it comes to Earth's temperature. We are much hotter than we were even throughout the medieval warm period. We are easily much hotter, and we are seeing those effects today. Now I want to focus on natural processes that change the environment. This should be a little bit of review from these extinction events. We learn how plants can cause and can drastically change the Earth's environment. From the late Devonian, we obviously see that vascular plants change Earth's landscape on a absolutely global scale. And we learn how evolution is a natural process. We also learn that volcanic activity and asteroid impacts too can alter the environment on a global scale. And I talked about those biotic and abiotic interactions changing along with the temperature of our planet. Now there are other causes I haven't talked about. What else causes natural climate swings? Well, this is a relatively newer understanding. And is that the sun actually has its own weather patterns. So depending on the temperature of the sun, there are these sunspots. In years of sunspots, we have warmer years on Earth. So, we think of the sun as just this homogeneous ball of gas that is emitting the same amount of heat from year to year, but that's not necessarily true, right? The sun is dynamic. The sun has its own weather patterns. And in some years, the Earth is hotter. And obviously, the Earth is going to be hotter because of these increased greenhouse gases. But some of that might have to do with the actual weather of the sun. Additionally, the Earth's tilt changes on much longer scales, as well as its elliptical orbit. So basically, the sun's intensity that I previously mentioned is on like an 11-year cycle, and its elliptical movement, like the actual shape of the the revolution of the Earth around the sun actually changes over much longer time scale. So over um, several thousand years, the Earth will move from this more circular orbit to a more elliptical orbit. Obviously, when it's more elliptical, you're going to have warmer periods because the distance from the sun to the Earth is diminished, especially along here. And then it's going to be colder on through these parts of the year. Additionally, you have the axial wobble change over several thousands of years. Now, I'm not refuting anthropogenic climate change here. I'm just telling you that there are some natural occurrences of planetary and our sun's interactions that do change the temperature on Earth. Now, it's important to note that these interactions don't have to do with the present day Anthropocene. I told you that yes, there's this 11-year cycle in the sun's intensity, but these other things that I've mentioned, the change of the orbit and the axial wobble. I didn't really mention the variation of the tilt, which is also on a multi-thousand-year cycle. These do not coincide with the present day Anthropocene. And I really like this figure because this shows the energy of the sun. So we have 100% of the solar energy entering our planet, entering the atmosphere. We have 25% of the energy is going to be absorbed by the clouds, and 45% is going to be absorbed by the surface. Of that 100%, you have 5% that's going to be reflected, right? And you have, so actually 25% is going to be reflected by the clouds as well. So there's a total of 30% energy just is completely reflected, right? Now this 5%, it is changing as the Earth heats up. We learn about the planet's albedo, and I really like how it shows, Greenland right here, how it's covered in ice, and we see the reflectivity off ice, right? And that's only 5% that is reflected off of high albedo surfaces. Now, that number is going to decrease as the temperature of the Earth keeps on increasing. Now, in terms of infrared energy or heat, we have 66% is outgoing. 70% is outgoing thermal energy that leaves our planet. The other 5% is going to be convected, up and down through the atmosphere and the Earth and the surface of the Earth. You get latent heat that just comes off of water. We get re-radiated heat from the surface, and from the greenhouse effect, you get this reabsorption of infrared radiation. So I really like this figure. It talks about these incoming solar radiation, and how, the different surfaces and substances are going to reflect and absorb heat. Obviously, incoming solar radiation, when it's absorbed on the Earth's surface, that actually creates infrared heat. right? So that light that then is transformed into infrared heat. So I really like that figure. This is this table talking about albedo. I really like this figure. Fresh snow has high albedo. Fresh snow is super white and it's going to reflect that light. Dirtier snow, it's not going to reflect that much light. It gets dirt particles in the actual snow. Those dirt particles are going to absorb heat, and that snow is actually going to melt faster because of that. But fresh snow has high albedo, 80 to 85%. There's a lot of reflectivity. Dense clouds have a really high albedo, like that figure on the previous slide suggests. Dense clouds have really high albedo, reflecting a lot of the sun's light. Water in low sun, so at an angle, so if the sun's coming in from the angle, the water actually has really high albedo. So the sun is going to reflect a lot of that light energy. And you can see, I've been on a boat, when the sun was at a kind of a harsher angle, and that you need sunglasses. That light is reflecting right off the surface because of the angle of the sun, and you can get really burned. Your eyes can get damaged if you don't wear sunglasses on a boat when you're nearing sunset, which is pretty cool that the angle of the sun has a large effect on albedo. Sand has lower albedo, right? Dark sand. I went to in Costa Rica. The beaches are black sand. So hot. I mean, I'm literally sprinting to the water because my feet are just burning. All right. So darker sand is going to have lower albedo than white sand, but sand is hot, right? So because when the surface, many of the time when a surface is going to be really warm, that means it has lower albedo because it's absorbing that heat. Forests have really low albedo. This makes a ton of sense, right? What are these organisms doing? They are absorbing the sun's energy. Because of that, they're absorbing light and they have low albedo. So when the sun is right over top of water, there is low albedo. There's not a lot of reflectivity, and that water is going to heat up the most right when the sun is overhead. Dark soil clearly has very low albedo. So I really like this table talking about albedo, light's reflectivity. I feel like I'm beating this to death. The greenhouse effect is the visible light emitted from the sun, passes through our atmosphere and heats the earth. Infrared radiation coming off of Earth's surface gets absorbed by certain gas molecules in our atmosphere. Heat energy gets trapped instead of being released into space, so our planet remains warm. So if our atmosphere didn't actually capture this re-emitted energy, the Earth's temperature on average would be about -6 degrees Celsius, right? So if there was no gas molecules trapping the infrared radiation, there would mostly not be liquid water. Along the equator, there would probably be warm enough temperatures for liquid water, but if the average temperature on Earth would be 21 degrees Fahrenheit rather than 57 degrees Fahrenheit. So much different planet. And thus, energy capture is necessary for liquid water as we know it. And the greenhouse effect is a common term to describe the capture of energy by gases in our atmosphere. I do have a link I'll put below so you can watch this animation. These are the three main greenhouse gases. They are red terms. You have CO2, CH4, and N2O, right? So CO2, carbon dioxide, CH4 is methane, and then N2O is nitrous oxide. They have climbed by over 31%, 151%, and 17%. Carbon dioxide is the most important greenhouse gas because it actually lasts for decades or centuries in the atmosphere. Methane and nitrous oxide are less stable, so they persist like a they persist for a lower duration. So they will denature. They will kind of split apart and bind with other molecules in the atmosphere in a few years. Whereas CO2, once you put it out in the atmosphere, it's going to be there for hundreds of years. So if current trends continue, CO2 concentrations, they will reach 500 parts per million, approaching 2 times the pre-industrial level. Before the Industrial Revolution, CO2 was around 280 parts per million. We are surpassed 400, getting closer to 450, and soon we're going to be in that 500 parts per million, which is not the best scenario. We have these contributions to global warming from different gases. CO2 from fossil fuel definitely dominates. CH4 or methane, interestingly, comes a lot from the herbivores that we eat. So we feed our cattle, our cows. We feed them a lot of corn. They eat grass. They evolved to eat grass, but they actually get really fat and they grow really fast when you feed them a corn diet. But they haven't evolved to eat corn, so they actually produce more methane on a corn diet than a grass diet, which is another interesting idea. And I just want to touch upon how if you're vegetarian, you're going to contribute an order of magnitude less greenhouse gases to our planet than if you are a carnivore or an omnivorous person. So there's a few factors involved here. So first off, people think I'm eating meat and that's it. But you know how many tons of plants you need to feed those animals so you can eat meat? So we fail to recognize the correlation between the plants, the animals that we eat, right? So, and additionally, the plants that we're feeding cattle, they are sequestering carbon dioxide, right? So when instead of just eating the plants, when we're feeding those plants to animals who are then respirating, who are then breaking down those plants back into carbon dioxide metabolically, and then we're eating them, and then they're producing more greenhouse gases through methane via their digestive system, you can see this positive feedback, right? And much of the deforestation across Brazil that has led to these insane Amazon fires are due to huge corporations that want beef lots. They want these huge areas to grow, to have cattle grazing, right? So just want to talk about humans' interactions with meat eating. Am I omnivorous? Yes, but I think it's important. I do take responsibility. I don't eat that much meat because I'm trying to reduce my greenhouse emissions. And the only thing I can do is focus on myself. So I tend to stay away from meat, especially throughout the week. I try to eat more vegetables. It's healthier for me and the planet. So just a little public service announcement there. Not really, because it has to do a lot with environmental biology. Back to this figure, we have this pie graph. Again, categorical data. You can jumble these categories around. The data still has the same integrity. You can see that the United States is the largest producer, second largest producer of greenhouse gases behind China. But China's population is much greater than American. So per capita, humans really, really do a job on the environment. 21%. All other nations besides these comprise of 25% of these greenhouse gases. So there is clear evidence that shows we are changing our planet, right? You can clearly see the correlation between the temperature and the greenhouse gases. Now I was talking about, these proxies. A few lectures ago, I talked about proxies. How do we know what the atmosphere was 5,000 years ago? Right? How do we know that? And there are several proxies that researchers use. One of my favorite to talk about are ice cores. So ice cores tell us about climate history. There are places on the planet, believe it or not, that have ice that was formed thousands of years ago. These places are, we call them permafrost, permanently frost, right? Many parts of these areas of permafrost are melting, but there are regions that have maintained frozen for thousands and thousands of years. So in ice, there are tiny little bubbles. Those bubbles actually are trapped air of the time of freezing. So researchers realize that if we take the gas from inside the bubble, we can put that gas in these devices that then read what the atmosphere was at the time, right? So like layers of rock, as you go down these layers of ice, you can actually date them. And if you have this really long core of ice and you date those different layers, then you could start and take samples of these ancient atmospheres through those tiny bubbles. So here is a researcher with an ice core, and they're gonna date those ice cores and those layers of ice, and then take out those tiny bubbles and analyze those bubbles. So the correlation between CO2 levels and historic temperatures really coincides quite nicely. So in the red, we have CO2 parts per million on this Y1. Y2 is temperature in Celsius, and you could see how closely these correlate, right? Now it's important to know that correlation does not equate to causation, but these data are strikingly similar, and there's just really no other explanation why these would pair up so well. We can clearly see that as CO2 changes through time, so does temperature. So CO2 is a great proxy for temperature. And so there are actually ice cores that go back to 800,000 years ago, right? Which is crazy. Wild. Now, the annual anthropogenic CO2 emissions, we see in this figure there are 4 scenarios, right? And again, we have this figure, we have these historical emissions increasing through time. And these 4 scenarios we have right here. And this is, the blue is if we kind of maintain, it's if we decrease our amount of emissions. Population's still going to grow, So, we are still going to have higher CO2 contents in our atmosphere as population increases, but you can see that the emissions stabilize if per capita we actually decrease our CO2 emissions. These yellow and purple scenarios are if we stay the same, or slightly increase our CO2 emissions, and then this red line, this gray area, shows that if we kind of increase like what is suggested in the data that we're finding, if we continue to increase our CO2 emissions, we are going to have this scenario. So again, another great example of extrapolation, right? We have, how different these scenarios can end up being in just the year 2100. So another great example of extrapolation. Now, the effects of climate change. Here's another figure showing extrapolation. So business as usual, if we carry out the same amount of CO2 emissions annually or per capita, then this actually equates to the sea level increasing. Now, if we have, if every country gets on board and we talk about if we try to tackle and mitigate these climate interactions and we reduce our CO2 emissions per capita, the oceans are still going to rise. So that's something important to realize. However, if we continue on the same track, we're going to get, over a meter, by 2100, our oceans are going to be nearly a meter taller, right? And this is it doesn't seem like that much, right? Like 2.5 feet of water doesn't seem that much, right? But the ocean is huge. The ocean is massive. And with this being said, we get we get water increasing, up to 1 meter. We get much of coastal Florida just completely going under. And this is only Florida. Think about how many coastal cities there are, super populated. Think about when a Category 5 hurricane comes in and gets, is about to hit land with the ocean already a few feet higher than it previously was. You're talking about complete and utter decimation of coastal cities, not to mention coastal ecosystems. So we need to get together, realize what's going on with our planet, and then act and become more consciously aware of your own interactions, right? What you do on an everyday basis. And then, again, a really important thing is to vote for policymakers that protect the environment, that protect and understand the current situation of our planet. So it's on a personal level, it's on a political level, and we need to, my goal is to encourage you guys to become active, to become passionate about trying to do something about this, and it does start with you. Remember that all paradigm shifts, paradigm shifts are going to be started by young individuals, young, smart, educated individuals. So I want you to feel empowered to do something about these interactions. I know that was a lot today. We focused on a lot. Thank you for your attention. I hope you guys are doing well. I hope you guys are happy and healthy. Stay up to date with that, with those October assignments that I just submitted, and I will post another video next week, probably another 2 videos next week. Thank you for your attention, and I will see you guys later.